So maybe this will clarify some stuff for people in general. On page 3. So we're looking at numbers 9, 10, and 11, that area. Okay, page 3. The lab, guys. We're on the lab. On page 3. So numbers 9, 10, 11 we're looking at. Okay.
Can you go over analysis?
I'm going to go over certain things. Hold on. So if I don't answer your question, then you can ask. For number 10, the idea again was that you were measuring. Okay, this was your measurement data table. First, if you remember, what was your mass for the first cup? 0.185. And the second one? Okay. It really does not matter that much, I guess. It doesn't matter, to be honest, guys. Okay. Next, the radius was your measurement. The radius was your measurement. The time it took to complete 10 cycles, those were your measurements. I can't give you that data. That's up to you. Now, again, when you have those two data values, you can then figure out the rest of it. So the next part. A lot of people seem to get confused, and I apologize if I didn't make this clear. Number 11, you're using the data table below. So for number 11, it says calculate the tangential speed, the centripetal acceleration, and the centripetal force. This is what this table is for down here, to calculate that. So you can do your work here, because I know you need a room for work, but your data and your answers are going in the table. So for example, for this one, which was 185 and 370, for Kyle, can you just tell me your group's data for this? For our radius?
0.57.
And then for radius for the longer?
7, 9.
And then the second one? Time,
10
sorry?
and 9.
10 seconds and then 9 seconds?
Yeah.
Okay. All right, so using her data, we can show a sample calculation. Take a look. For speed, speed is always distance over time. Distance over time. Now this says 2 pi r, because 2 pi r is one what? Circumference, or one circle. Okay, 2 pi r. Well, how many times did we go by? 10. So when you calculate the speed, you remember you want to be using 20 pi r over t. R is right here, t is right here. So you're going to be getting the speed. So see how these are different tables? This kind of goes along with it. So if you want to extend this table up here like this instead, if it makes it more clear, and call this speed, acceleration, and then force. That's what you're doing here for this table. So I apologize. Next year I think I'm going to make it one table because it seemed to be a little bit unclear. You're finding the speed, you're finding the acceleration, and you're finding the force for both scenarios of the previous problem. Okay? Start. Why is theirs?
Yeah, it's like...
It depends on where you started by holding the thing also. Remember, you could have started with 3 rubber bands, you could have done 2 or 1. Every group is different.
You did 1 rubber band?
No, they chose to do 1.
Ridiculously large.
Because you had 2 rubber bands. Okay? It turns out to be yes. Now, please remember when you're doing this part, if you have other questions, ask me, that's fine. When you're doing this portion for acceleration, it says v squared over r, right? V is velocity, but in this case, velocity and speed are the same thing. Okay, we talked about this last time. Velocity and speed are the same. Here, for force, it's mv squared over r. mv squared over r. M is the mass, and then you multiply by v squared over r. So again, you're doing this for 2 scenarios. Now, once you finish...
So just get the velocity formula from out of our notes. It's right there.
It's right here. That's what I'm trying to show you. So, like, this is the speed formula, right? For this one here, use the same thing for velocity, because speed and velocity happen to be the same here.
Okay. The same?
No. I'm telling you, the speed that you get here is really velocity. It's the same thing. It's really called speed. I have some in my throat.
So just to confirm, put that over radius. That formula.
That formula squared over the radius.
Okay.
Because it's v squared, right? Yep. 20 pi r all over t. That whole thing squared over r. Continuing, once you get through this table, you've got some discussion questions for you to interpret on your own, please. Again, just ask you about the effect of certain things on it. In the next part, what your goal...
Were there any right or wrong answers?
Well, no, because like
There are blatantly wrong answers, but there are many right answers. There are many ways to interpret it. Okay? Based on your data, you might have a different interpretation than Star's group. Maybe your data was successful, hers wasn't, or vice versa. You never know, right? So you have to interpret your data. For the second half, your mass was supposed to be what here? 0.185. This one was supposed to be the smaller mass. How come? What was the reason? What did we do with this one? We spun it faster. Remember, this one, the goal was to spin it faster. So there should be, this must be, or sorry, it doesn't have to be, but if you use 370 here, I don't know how you could have done that, because spinning that one fast was almost impossible. It kept exploding everywhere. So here, your time should be shorter than your last one. The time for your group was 9 seconds for 185, right? And then what did you get for here? 8 seconds? And if you're spinning faster, the time should go down from the previous experiment. Okay? It might not be a great difference. It might not, because it was tough to spin that fast. Okay? Now, same thing again. Same thing again. You have a measured radius. You've got a time. Find all three things. Find speed, acceleration, and find the force. Now, the last discussion questions are pretty much asking you to take a look and say, what happens as the speed increases, okay? What happens to your length of your radius, and what also happens to the force as the speed increases? So what can you compare this to? The other one. Again, remember, this is 185. This is whatever you calculated. This is whatever you calculated. You already did a 185 in the last one, didn't you? And it was gone, you went pretty slow with that one. This one you went faster. So compare this data entry, or these three data values. Your speed should be higher. Your acceleration, I'm not going to say what it is, should be different. And your force should be different. So based on these values, answer the question. So again, you have to go back to the other experiment and compare it to that data. I wasn't going to make you do the same thing twice. So again, you're comparing 185 at a faster rate to 185 from the beginning of the experiment, which was at a normal rate, or a slower, relatively speaking, rate. Okay? So based on the comparison, answer the last two questions. The questions, again, there's only 5 questions total. A lot of it is after this stuff. Any other questions? Okay, when are they due? Why don't we say Thursday or Friday? What's easier?
What did you say?
Friday?
Yeah.
Okay. Friday's fine. It's up to you guys. You decide. So don't tell me on Thursday you have another thing to do Friday. I'm giving you Thursday or Friday to hand it in. Either day.
Also, we're going to do it Thursday night.
There's only 5 minutes.
Seven.
God bless you.
I got that.
Potato chip. Barbecue.
Now, we've talked about this, guys, several times. It's your weight. Remember, the gravitational force, or the force due to gravity, this is your weight. What we're going to really do today is discuss the gravitational force, not just between us and the Earth, but maybe between the Earth and the Moon. So where the tides come from, for example, or the gravitational force that's between the Sun and the Earth, what keeps us revolving around the Sun. So gravitational force is much more expansive than just our weight. But for us, when we say we're being pulled to the Earth, it's the gravitational force between the center of the Earth and the center of our body. Now the center of our body might be a different location depending on how tall we are, okay? But you're looking at the center of mass of it, okay? So what we're thinking about now is if you have any two objects, does not matter what the two objects are, does not matter what their shapes are. If we know that their center of mass is at two different locations, let's say that's that center of mass, that's that center of mass, and we are able to determine the distance between them, we can determine the gravitational force they exhibit on each other.
This would be a bit theoretical.
Mhm.
Instead of us being pulled to the Earth, can we just push us down instead of being pulled down?
The gravitational force is really thought of as a pull because it's the attraction between two objects. And if you're somehow getting drawn toward me, it must be a pull, right? A push indicates that you're moving it in the direction of.
Yeah,
You could theoretically call it a push if you wanted to, but you just hear it as pull. If that answers it easily, because I understand what you're saying completely, but it doesn't really matter. We don't call it one or the other. Actually, we just call it gravitation. Okay. So again, what we need to know again for this, for the gravitational force, if we know the mass of each object, okay, we need to know the mass of each object and simply the distance between the centers. Okay, those are the two things that we're going to need to determine the gravitational force between any two objects. For example, Star's calculator and these pieces of paper are pulling on each other right now. They are. But their masses are so small that the force is negligible. I don't feel it. I don't feel them pulling together, but they are, believe it or not. That computer and the mouse that's next to it, they're pulling on each other. Every object is pulling on each other. But when the mass is so small, and we can do examples of this, and I'll show you, you'll see that it has no effect.
Oh, is that right?
Okay.
One at a time, guys.
As we had a mouse
Listen, guys.
As we had a mouse pulling on a desk and like gravitation, but how are you holding a piece of paper in the calculator? Like
No matter-
doesn't need a magnet or something?
No matter what, if you have a mass of each object, they pull on each other, always. Whenever you have a mass, they just pull on each other.
And we
Now-
can use that finding like how the moon makes waves?
Correct. Not waves, but tides. They're
Yeah,
different.
tides.
The wave comes from the friction between the sand and the water as it's pulling up. And there is some sort of gravitational force, but it's the tides that show difference. And we'll explain that. Julie.
What I was going to say is, like, you talking about gravitational forces. Don't you know how, like you have like a clump of dog fur?
A what? What was that?
A clump of dog fur.
Okay, dog
And-
fur.
Yeah, don't you know how when it sheds and you know how?
That's static electricity. See, like it's stuck to stuff and gets held onto them, you're
yeah,
saying?
and then you know like.
And it like lumps together.
Then you take it out and you drop it. It automatically like it's like it goes.
That's static electricity, which has to do with a force, but it's static. It's different. Okay, that's an electrical charge. It's like the fact that there's an unbalanced charge. There's more electrons in the hair that are present. That's like when you take a balloon and rub it on your hair and then put it on the wall and sticks, because you're charging the balloon with a charge, and then it's gripping on with static electricity because its mass is so little. Okay, it's a little different though.
We like
No
touch
water,
stuff,
though.
we shock.
That's static electricity also, yep. It's an imbalance of charge, and what you're doing is you're allowing that charge to flow through your body. There's a mix-up, and there's a ton of charge on something, and then you touch it, and you're like, ah! Well, all that charge went through your body into the ground. You grounded it. So, but that's physics too. That's electricity and magnetism. There's two types of physics. Physics 1 is the study of movement, the study of objects, the study of forces. Physics 2 is the study of like electrical circuits. If you're looking at a force field, if you're looking at like in the nucleus, you're looking at protons and electrons and how they interact with each other. That's physics 2. Then you go on and just look at other stuff. You can look at like nuclear physics, subatomic physics, quantum physics, all different types. So there's a lot. But again, we're looking at mechanics here. That's why these things are good things to discuss because they do here. Adolfo, still question? You got it.
Yeah, say for example you had two, say magnets. One would have the negative charge and one would have the positive charge. If you connected that, or the other way around, one positive, one positive, will that still be the same kind of gravitational force?
Magnetic force is totally different. That's a magnetic force. Gravitational force and magnetic are two different things.
So it won't rely on any gravitational force.
No, sorry. Each pole is magnetically charged on the Earth, so you have this contour of electrical charges. If you've ever seen that before, if you look at like images of the Earth, they show like this contour called a gradient, and that's the electrical charge that's north and south, as in like positive and negative. But that's not gravitation. It has nothing to do with that. Okay. All right, so let's get back to this. So again, if we know the distance between the two centers, and we know the mass of each object, we can calculate the gravitational force. Now, you might ask, okay, well, first of all, what are the units going to be on this? If it's a force,
What are the units of this?
newtons. Very good, newtons. So we're going to have a newton as our answer. So for this one, what I'm going to do is I'm not going to go through the derivation of the formula. Okay, I'm not going to go through where it comes from and all that other stuff. But what I want to start with is a simple example of gravitational force. So let's say hypothetically, and you can draw this, it's very simple to draw. Let's say you're on the surface of the Earth, and we'll say that let's say we're looking at only like the upper part of the Earth. The rest of the Earth would continue. So we're looking at maybe like this is the North Pole, and then there's like Antarctica, or not Antarctica, there's Arctic Circle. Okay, so say there's all the ice, and it's a polar ice cap. Okay, so we have ice here. We've got like, this is where Greenland is over here maybe. This is like Canada and stuff, and the U.S. goes down further.
Wait, Canada,
Europe. Okay. So, imagine if you will, that there's a giant station at the North Pole with a slingshot on top of it. Okay? So we got a giant slingshot on the North Pole.
It's from Legend. It's from
Okay? So the slingshot can be pulled and launched. That's a pretty good drawing. Thank you. Thank you. Now, if we pull back on this enough, okay, if we pull back on this enough and let go, the object will shoot off into space, okay? And that means it's escaping the Earth, right? If you pull on it not that high, though, say you only pull a little bit back, it'll start to go, but then what will happen? It'll get pulled back toward the Earth, right? And it'll follow that parabolic path that we've looked at, projectiles, parabola. Okay. So what we have to think about is this. When it comes to gravitational force, it's the thing that's holding you to the surface. If you could somehow get out of that, it's called the escape velocity. Okay, so I want to write that down here.
So they look at that when they're trying to get out the
Yes,
atmosphere?
that's exactly right. So for like rockets and stuff that are going for NASA, they always need to know at what angle, they have to know like at what angle and at what speed do they launch it so that they have enough escape velocity. Okay, so you're always trying to overcome the force of gravity between the Earth and the object because the Earth is the nearest object. And when they get near the moon, and when they start to land on the moon will start to pull them down. But on the moon, we know it's only 1/6 of gravity. Remember we did that example? And I was telling you, as you jump on the moon, you kind of jump like this. Okay, because the gravity on the moon is not 9.81, but it's more like 1.5 or 1.6. Okay, so you're a lot less weight on the moon. You feel like you're a lot less weight. Same mass, but a lot less weight because of gravity. So if you can escape it, it's called escape velocity. Because again, you're getting pulled back. Start.
You said overcome between what and what?
The force of gravity between the Earth and the object. Whatever the object may be. Okay, a rocket, whatever. Now, in order, Kenny, this way, here people. In order to determine what that velocity is, in order to determine the escape velocity, remember, velocity is related to acceleration, and acceleration is related to the force. Because force equals ma, there's your a, and acceleration is equal to the velocity over time. So they're all related to each other. So to figure out this escape velocity, they needed to figure out, well, what is the force? Okay, what is the actual force that's being pulled between here? So, just to give you this formula, okay? We're not going to go through a derivation of this. To give you the formula, we have G, M1, M2. Now, this is where it gets a little confusing. It's called R squared. Okay? Now, R is not the radius. And in physics, they've done this for a long time, which confuses the heck out of people. And I'm giving you this so you know. R here, in this case, is the distance between the two centers. So remember in the last example when I had this up here like this? This distance, they're calling it R instead of D.
So it's a length,
It's been this way for a long time, guys. And later on, we're going to start studying objects that are orbiting, and we'll see how R kind of makes more sense with that. Okay, but for now, just write down, please, for this formula, just write a little, whoops.
So the length
Just write a little note, please. Write a note to yourself. R is equal to radius. R is equal to, not equal to radius.
It's the distance.
Okay? The radius is not R in this case. The radius is not R. Now, think logically though. Just use logic. Forget about nomenclature. R, S, D. They're all position or velocity or position or distance or radius. Doesn't matter. Think about it logically. M is mass. M is mass. G is something we haven't talked about yet. R's got to be something, right? And for these kind of problems, the distance apart you are changes the force you have. That's why, like, if you're up higher in the mountains, you feel like you're less weight because your distance between you is getting bigger. So as your denominator gets bigger, your force gets less. So if you go up higher in the mountains, and there's like, for example, there was an Olympics at one point where the high jump, the set record is like at an elevation of like 4,000 feet though. So the person that has the record for the high jump, it was at a high elevation. And you're less weight, theoretically. You really are. And there's always been like an argument that because the person was up on the mountain, they were able to jump higher in that Olympic game. Which is really not true at all because it's negligible. If you don't notice, you really don't notice the difference in your weight if you're here or at the top of the mountain. You notice differences like air pressure. So when you if you were to go up somewhere and you cook food, it's different cooking up in the high mountain than it is here. Temperatures are different, pressures are different, it's a little bit off, which is kind of weird to think about. So like if you're at a really high elevation, you have to change some stuff around. Now, we're not going to start looking at that right now, but what I want you to get the idea is that as the distance increases, the force between them goes down because the radius is in the denominator, or the R value is in the denominator.
Is this just distance away from objects or distance from the Earth?
The distance between the two centers, whatever that may be. It doesn't have to be the Earth. So for example, the same example as before, there's a force between these two. Okay? Now the force is getting stronger. Now it's stronger. Now it's weaker. Now it's weaker. Now it's weaker. Just think logically, right? If you're closer to something, you have more, in a sense, attraction to it. And I'm not, I'm talking about objects now. So these get stronger force, weaker force, weaker force, weaker force, and so forth. Okay? So similar to magnets. That's exactly like magnets. The magnetic force, we're going to look at when we talk about magnets, if we get to it, we're not have time at the end of the year. We're going to see that also has an R in the denominator, or the distance between them in the denominator. So write yourself a note, please. What did we just say? How could you summarize what I just said in like 5 words? Or 5 things, that's it.
I'll record
As, I'll give you the first word.
As
Objects get closer
Together,
together.
then stronger.
As objects are closer together, what?
Force
The stronger the force, right? So we could say this. So watch this. As R, as the distance between them, as they get closer, as R gets closer and closer to 0, okay? Just listen, just listen. I said symbols or words, that's all. So as R gets closer and closer to 0, okay, the value of the force increases.
cheating. That is cheating. And it's
Okay.
okay?
Again, as the distance gets closer and closer, the force goes up. But think about this, guys. This is like limits. And a lot of you have learned limits already in pre-calc. In calc, you know you've learned limits already. This is a limit. As R goes to 0. As the distance between those objects is closer, the force is going up dramatically. Until they get almost so close that they can't get any closer at all. Like me on the Earth. Theoretically, I can get closer to the center of the Earth. How would I do that?
Dig a hole.
I gotta dig a hole or sit on the floor, okay? Or I gotta, go in the ocean and dive down. You get closer, sure, but eventually you would die, obviously, for other reasons. But again, I'm pretty much as close to the center as I can get right now, okay? Even going below sea level is not gonna change that much. It'll change pressure because that's different.
So you're saying that if 2 objects are touching, that's when your gravitational force.
Is that the maximum, really?
Alright.
It's the highest it can be. There's a max level. So it's like there's a limitation of the force, okay? The force might look like this, guys. The force is over R squared. So as R goes, let's do it this way. We'll call that the R axis, we'll call that the F axis. As R, listen please, if R is out here, if there's a large distance, then the force might be small. Then it gets bigger, then it gets bigger, then it gets bigger. What do you see is happening here? What is that called when it goes up like this? An asymptote, very good. Where's the asymptote? It's at R equals 0, because that's what would make the denominator 0, or would make this undefined. Okay, but what you need to really remember is this, okay? Please remember that. And that's from the formulas we're getting at. Okay, from the formula. As this value increases, okay, this value will decrease. As this value decreases, this value will increase because they are inversely proportional. Inversely proportional to the square.
I have when it's to do with like density of water and like how they make submarines and they go like lower to the water. Is this have to do something like escape velocity or no, nothing at all?
Some rains?
No, because you know how submarines go like deeper and deeper into the water.
Submarines, thank you. I thought you said summer rains. Submarines go deeper and deeper into the water.
I mean, water too much spent.
They go deeper and deeper into the water.
Deeper to the water, so the pressure changes.
That's the amount of water above that. If you look from below and you shot a profile, if you extruded the shape straight up, thinking of the submarine as the base of the shape, and you made a prism straight up, the amount of water indicates the amount of pressure.
What
It's
about
fluid.
also what submarines are moving? Doesn't it also change in a way? Cause,
Sure. The velocity will change. Has to do with that will be force of drag on it, which creates more pressure and stuff. Yeah. But for now, we're not even talking about that stuff. That's fluid mechanics, which is coming up. We're doing fluid mechanics soon too. I've got a really cool video for you guys, like the best one I think out of all the videos. But when we get to fluid mechanics, so you got like 2 weeks to see it.
Do what we're doing. Exactly. The next chapter.
The next one's really good. All right, let's go to So back to our formula. Back to our formula now. Okay, remember, again, just to list these, if we're listing in our formula, M1 is the mass of object 1, M2 is the mass of object 2. Okay, again, doesn't matter what the objects are, it could be 2 calculators, we'll figure that out later, we'll show how it's negligible. What is R again? Very good. Distance, what? It could be a calculator and a water bottle. If they are, it just happens to be that. It doesn't make a difference though, because this is pretty much just as light as that, right? So it has no effect depending on the object. Oh, if the masses are really small, if they're both really small, and then you'd be squaring a small number. Think about it, squaring. The linear distance, yes, not the curved distance.
I mean, like, you said the objects, like the objects have to be like horizontal, either be like.
Okay, if they're this way. If they're this way. If they're this way. So this way. What's the distance either way? Does it matter? Does it matter the orientation if I'm at the same distance the whole time? Right? Take like here. Let me give you a simple example. Christian, it's a great question. So object 1 is my key. Object 2, let's say there's a ball at the end of here. How far apart are they? Estimate. About a foot. Good. So let's say they're a foot apart. Now, if they look like this and they're a foot apart, the ball has a mass, the key has a mass. If I go like this, have their masses changed?
No.
Has the distance changed? No. Has it changed now? Does it ever change?
I mean the height. It's the height. What?
So if it went like this
It
now?
didn't matter.
Yeah, because I mean, like, aren't you saying that gravity is relative to the height?
Sure. So if there's 2 objects is different, like for example, my center of mass is probably right around here. Jason, if he stood up, his center of mass might be over here. Right? Yours is a little higher. Sorry, Jack. So again, my mass is here, his might be here. So the distance between his center of mass and the Earth is more than the distance between my center of mass and the Earth, but it's negligible. It's not even important. That's the idea between us and like a high mountain. Even that is negligible. And we'll go through some examples of why.
So I actually just had a question. So you know you were I could be making a statement too, but I'm saying. Make a question. But you know how you're saying your center of like the center of your body was like here and his is higher. So when it looks at the distance between the 2 objects, is it like looking at like the shorter distance?
Always the shortest distance between 2 points, which is a line. Yep. Always the shortest distance between any 2 points. And the fact that the Earth is a sphere doesn't matter where you are on the Earth, really. I mean, it's oblate. It's not a perfect sphere. Okay? The Earth is actually kind of stretched.
It's not perfect.
Okay, it's not even close to perfect. Not even close. The poles are kind of like squished. I mean, the tilt is off also. It's at a 23.4 degree tilt, and it's pushed in a little bit. It's kind of oblate on the ends. It looks like it's perfect, but it's not really.
Well, because we're only listening from the TV.
Sure, and also when you're out far enough, everything looks good, right? You know, like, I mean, if you had a function that looked like this, say that was the function, it's quartic, you zoom out enough and you keep zooming out further and further, eventually that looks like this if you zoom out real far.
Oh yeah, but
Right? Same idea. That's why Earth looks like it's a sphere when it's really not.
That's how it works. That's when you get close enough to the line, right?
Like on a graph?
Oh, yeah,
Oh, yeah.
Like when you graph a function, if you keep zooming out, eventually it just looks kind of like a curve, right? You don't see the intricacies, same with the Earth. All right, now,
The
value G. The value G here. This is an experimental value that was determined. Okay, just like, for example, if we know pi is always circumference over diameter, right? It's always whatever the circumference of the circle is over the diameter. And we kept dividing it over and over, and we kept seeing that no matter what object, and we did this with the first lab of the year, no matter what object, if you take the circumference of the diameter, you always get 3.1415. That's where pi came from, and so forth and so on. This number comes the same way. They're able to determine the force between the objects, and then knowing these values, they were to determine this experimentally. So here, I'm going to give you the number just so you know, okay? The number is a constant, yes. 6.67 times 10 to the negative 11. Okay? It's a very small number, so for those that are fearing scientific notation, you got to get over that fear. Because you're going to have to use that little E button in the calculator, and we'll go through some examples of that to see how easy it is. Now, the units on this, I want to see who can figure this out, and this is a challenge. I'm going to give you about 2 minutes. I need to think about this. Let's see, if I tell you, this units are obviously newtons, correct? Because it's force. We know the units of mass, and we know the units of distance. If you know these three units, figure out what this units must be to give you newtons at the end. Go. Figure it out. Again, you know the units of mass. What are the units of mass? Okay? I'm not going to give you the answer, and here, what's the units? Okay, and you're going to square it. Keep that in mind. Okay? Because you're squaring it. So tell me, what must the units of G be? Write it down. What must the units of G be in order for you to get newtons as your force? If you have it written down, I'll come by and check. Again, you want to check? Write it down.
What makes it a Newton? What makes it a Newton?
Google it.
Yes, right now.
Can you get newtons like that?
Oh my gosh.
Again, guys, follow directions. If you want to check, write it down.
A meter.
Anybody else?
Oh, wait.
It's broken.
What are newtons? Chris, you know what newtons are?
How are your assignments?
I don't know what. I know what it is.
Oh my God,
Come on, guys. Be able to get this. It's not a tough problem.
I just don't know what to get everything.
Chris. Who would eat this? I would. What?
And I know once, earlier on,
Very jolly.
It's just me and Katie. You know that's
Who's your supervisor?
I like your argument, but no.
He just said.
You said not.
All right, let's go through how to figure this out. Here's what you do.
You find out what a newton is.
No, guys, it's much easier than what you're all thinking right now. Okay, watch. You start. You put newton over here. Okay. For G, just put like an empty box. Put your units of kg here and kg there. Put your units of meter here and put a square there. Now, at this point in time, if you don't want to have You want your answer to have only newtons, only newtons. So you don't want all this other junk, right? So what must these units be to get rid of them? How do you get rid of 2 kgs that are in the top? Put 2 kgs in the bottom. So that starts with those units. It's going to have a kg squared in the bottom. Good. If I want to get rid of 2 meters or meters squared in the bottom, how do I get rid of it? Put it in the top. So put a meter squared up top. And then if I want to have newtons as my answer, if I want newtons over here and it's on the top, not the bottom, how do I get newtons over here? Put it up top. So your units are Newton meters squared per kg squared. Newtons meters squared per kg squared. And remember, just like on your test last time, guys, if you want to indicate multiplication with units, you sometimes see it look like this. Okay, and some of you got confused on this. I showed it once before, and it's all one time. Again, this is really newtons times meters squared over kg squared. When you show units, it looks like a minus sign, even though this is newtons times meters squared. I know it's the weirdest thing ever, and I personally don't know where it came from. I can look it up, I'm not sure. But for some reason, a long time ago, when writing units, the adoption was made where you have, instead of showing a multiplication, whenever it's multiplied, they put a hyphen. It's not a subtraction, and you'll notice it. If you see it on like a test, it'll look like this. It'll say newtons, it'll be a long hyphen, and then it'll say meters squared. Whereas like a subtraction sign really looks like this, newtons, and then it would be like minus meters squared. That's like a minus. That's a hyphen. I know it looks weird, but this is the truth. So the units in the end for G are Newton meters squared per kg squared.
When you say per kg,
Per means division. Newton.
that's why we squared it.
That's exactly right, because look, you're going to have a mass and a mass. And to get rid of these 2 kgs, you need a double kg in the bottom. That's where those two come from. But they both have units of kg still, don't they?
Yeah.
So the units still cancel. The numbers don't matter. I'm not caring about the numbers. We'll get units only.
You have to write it with the kg.
No, you can write it with a time symbol if you feel more comfortable. I don't mind. I would not put it as nm squared. Here's the reason. If you had like lowercase nm, and I know you're not going to, but that's a nanometer. There might be another terminology for a capital N. So I would put like a dot or a hyphen, either one or the other. Okay? Not at the top. It's just it's a longer hyphen if you're going to actually draw it out. Okay? Again, it's not a subtraction sign. It's a long hyphen. That's all it is, which really means times. Again, this means times here. So if you want to write it like that, or if you want to write it like this, I don't mind. To me, it's the same thing. Okay? And you're never going to really be told that this is wrong. It's just that if you see this, I want you to know where it comes from. So again, using this formula now, let's go through an example of what we can do with this. Okay? Again, all we've done is show them where the formula is. Now let's go ahead and use the formula. So, let's say we have... Let's say we have 2, I don't know, pool balls on a pool table. Okay, so we'll say there's a stripe and there's a solid. Now, let's say we know that let's say theoretically that the cue ball, we'll say this is the cue ball actually. Okay, the cue ball. We'll say the cue ball has a different mass, just to make it up so it makes it a little more difficult. So say the mass of the cue ball is going to be, let's say, 300 grams, and the mass of the 8 ball is going to be, or the whatever the other ball is, let's say 200 grams. Okay? God bless you. We'll figure it out in a sec. We also know they're separated by some distance x. Okay, they're separated by some distance x here. Now, so here's the problem. If the force between the pool balls, the force is, and it's going to be a very small number, because again, the force is almost negligible, and this is the actual value of the force there. So take a look at this. you're talking about adding like 10 zeros to here. So 0.000000008 newtons. Okay, again, you're moving this decimal, how many spots? 11 spots to the left. So think about how small of a force this is. That's where the idea of a force being negligible comes in. Okay, this is no different than like the example before with the calculators.
So by negligible, what do you mean? Just like debatable?
No, just drop off.
Okay.
So,
Okay. Yes, as delta x goes to 0, that's exactly what it is.
Oh, okay.
So here, okay, so if the force between the two pool balls is that, find, oh no, we know G, find the distance between them.
R. So the X.
Okay, so I called it x, but what did we call it in the formula?
R.
So it doesn't matter really, right? In the formula, when you write it down, write it as F equals, again, G, M1, M2, and it's usually over R squared. So what? Call it x squared now. It's just the distance, that's all that matters, right? Again, it's a variable for that reason. It doesn't matter what you call it. So we're trying to figure out the distance between them, the R value. In the diagram, it's called x, so we call it x. No difference. Now, we know F. We know G. G is a constant. From now on, you always know G. You don't ever have to memorize it. It'll be given. You know the masses of each. So solve for x squared. So how do I get x squared by itself? And then take rid of, how do you? Very good. Just switch, please. Again, you're going to multiply this up, and you're going to divide the f down below. So just switch the spots.
Mr. How will it always be when they say distance? How do we know it's from the center? It's from the center of both.
They'll give you in the diagram. Yeah, the diagram always say this star. Okay? Absolutely. Star makes a good point, guys. How do you know that the distance is between center to center? It'll be given in the diagram. If it's not star, we'll look at examples of that, but we're not there yet.
I thought it was always.
But we'll talk about that. Yeah, it is, but I'm saying, what if they gave you a distance from pool ball to pool ball? Then you have to add on 2 radii. Add a radii on here and add a radius here to get the full distance. Okay?
Yeah, okay, I see what you mean. It's just
Now,
okay.
continuing. Convert, please. What is this? Good. 0.2 kgs. And this is really 0.3 kgs. Again, how do I know that? I move the decimal 3 spots because I'm going to kilo. I want to go from gram to kilo, so I move it 1, 2, 3 spots. I get 0.3. Again, 1, 2, 3 spots. 0.2. Continuing down, we get x equals the square root of this whole thing. Again, the square root of G, M1, M2 over F. I'm going to do this on the calculator with you. Please check on your own.
Do we put it to the ground? When you put it, you still raise it to the power, you just put a left negative below it. Okay.
Everybody see at this point, I'm just filling in numbers, okay? Again, for now, I'm going to suggest to you guys that you just type in your calculator this way and don't do any cancellation on your own, because there's a lot of common mistakes that people make, and I don't want to start worrying about that right now in this class. So my suggestion is to simply just type in your calculator at this point. But again, theoretically, Bridget, yes, the 10 to the negative 11s, they do cancel. Okay, both of them cancel because they're factors. But I don't want common mistakes to start happening, so please just go to this point and type it in.
It's gonna give it to the E too. Were you gonna number?
Your answer should be a number, yeah. Let's go through this. All right. So from the last one we just had up a minute ago, we got the square root. So please start with your square root here. The square root of, so second square root. Do it all in one line, please. Don't do it in separate lines. Do it all in one line. Now, I want to take the square root of a numerator over a denominator. So I have to open my parentheses for the numerator. That opens the parentheses for the square root. I add another parentheses for my numerator. That's opening my numerator right now. Okay? Now I need to multiply 3 things in the numerator, close it, divide by the denominator, close it again. Again, I'm opening the numerator. The first number is 6.67 second e to the negative 11. Okay, 6.67 times 10 to the negative 11. That's the first
It
number.
already counts as that, right?
That's the first one. Times 0.2 times 0.3. That was all in the numerator. How did I get to e? Sorry. You press second and then the comma. The comma's right here. It's above the 7. And you see a capital E twice. The capital E twice really means times 10 to the. So this is 6.67 times 10 to the negative 11. Okay? Times 10 to the. All divided by... Get where? Second square root to start. I'm going to open the square root first, okay? So, divided by, we want to have a denominator, okay? The denominator was what? 8.92. Okay, that's the denominator. I close the denominator, and then I close the whole thing. Now, a lot of people, guys, a lot of you guys forget the parentheses there. Count. Here's how you can always do it. Count however many parentheses are open. Count however many are closed. If they don't match up, you miss a parentheses. Let's go through this. Watch. 1 open, 2 open, 3 open. 1 closed, 2 closed, 3 closed. We're good to go. Okay? Go ahead, hit enter. You're going to see 0.2118. Now, what are my units going to be? What are we solving for, people? Very good, Karen. Why is it meters? Distance between the two objects. So your answer, which makes sense, 211 meters, that's about 21 centimeters. Think about 21 centimeters. That's this far. That's how far pool balls are apart from each other. This problem does make sense. It's logical, the answer. Okay?
Mr. Howard, we're going to do 2, 1, and 2.
Say again?
Oh, this is a round, we just stop.
Sorry, yeah, if you round it, absolutely. You're absolutely right.
We don't have to round, we just take.
I was just being lazy, but you should round if you're going to round. If you're going to stop, just round it, yes. Okay? I would probably have done 2118, to be honest, for myself. Okay? To give me 2 decimal spots down here. Now, the idea here is that no matter what you have in this problem, you could solve for R, you could solve for one of the masses, you could solve for the force between the objects also. Let's go ahead and take a look at an example now. Okay? And what I want us to do is this. I want us to figure out how we can determine our weight using this formula and then verify that weight by using our mass. You know how we said like F equals mg in the beginning of the year, it's weight, W equals mg, we get a number?
Oh, okay.
We can use the same formula and get the same number. And I'm going to prove that to you now.
But do we
Okay, that's what we're going to go through.
change the F in the front to MA?
No.
Mr. Howard, which one?
Either one. 212 meters or 21.2 centimeters. It's just converting. Again, this is in meters, Star. Unless you double it. Because you need parentheses around your numerator, and then you need parentheses around your denominator. In this case, if you didn't have the extra parentheses, it wouldn't matter, it turns out, because they're multiply, 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 divide. But the minute you have a plus sign in there, it wouldn't work. So I'm just trying to make you guys safe. Whenever you put in a fraction in the radical, put your parentheses around the numerator and the denominator. It's just for safety.
I keep getting the errors.
What does it say?
So you know how like what's it called letters that we know?
That's a minus.
Chris. What is the letter?
Guys, if you get an error, did anybody get an error when they typed it in? If you use a minus sign instead of a negative sign, you're going to get an error also. Be careful with that. Go, Okay, that's our value we're going to use. Now, do we have to change it to centimeters?
What?
Depends, man. I mean, you don't want it, you don't have to. If the problem says answer centimeters, I'm just trying to give you logical statements. That's all. All right. So let's say, for example, we have a person, and the person has a mass of, let's say, 80 kilograms.
He just got back to McDonald's, so make it 120.
Now, if you want to find the weight, everybody, we know the weight is equal to the mass times gravity, so it's 80 times 9.81, and we can solve and get our weight. Okay? Again, is that clear? We've done that many times before. That's the weight of the object. Now, let's go ahead and prove that using our new formula. Find the weight. So we know we need to figure out what the mass of the Earth is.
Yeah, so we look at the core of the Earth, right?
We need to know the
What is the center of the Earth?
we really need to know the radius of the Earth, because think about it logically. The distance between me and the center of the Earth is pretty much just the radius. Think about where I am, right? I mean, come on. The radius between the center of the Earth and the surface is a ton of miles. And then suddenly I'm like, 5 feet tall. Is my height going to have any effect, really? So the distance between me, so here's the person, or here's the Earth. The person, you wouldn't even be able to see. So when we draw images, we always draw them like this, right? Just to show that there's a person there, but clearly that's like a giant person. Like thousands of feet tall if you're going to look like that on the Earth. So the distance between the center of the Earth and the center of the person is pretty much the radius of the Earth. Okay? Now, the radius of the Earth is,
You know what?
where'd you go on it? Okay. 6.372 times 10 to the 6. And those units are meters, which is 6,372 kilometers. Okay? Kilometers. Now, the mass of the Earth is 5.97 times 10 to the 24 kilograms. Look at the mass of the Earth times 10 to the 24. Okay? So, do you think your mass really has much of an effect here? Okay? Again, it's the mass of the Earth that's causing this pull. So think now about, imagine if you had you and the calculator again. It's pretty much non-existent. It's this Earth's mass which is giving you that pull. So go ahead, plug this into your formula, please, and calculate. Again, remember your formula. Okay? And remember, G is 6.67 times 10 to the negative 11 newtons. Whoops, kg or M?
What is the gravity?
What do you mean?
Shouldn't it be 9.81?
Yeah, that's what we're going to talk about tomorrow, where it comes from, right? Or Thursday, rather.
I mean, for this, shouldn't that be?
What I want you guys to do tonight, besides finish this problem, you have 2 nights. Listen carefully. Folks, stop talking and listen for a second. Finish up this problem, get the force. It should be the same as whatever you get for this answer. Also, I put it on the sideboard. Look at numbers 1, 2, and 3 on page 247. Okay, 247, numbers 1, 2, and 3. Okay, you have 2 nights. 2 nights to do this. Make sure you come in on Thursday with this ready. Hurry up.
You do look into some guys.
You know what you were saying?
Go to the bathroom.
I feel like the second guy.
How is this person reading?